Okay, so let's start for today's lecture. So, in the last lecture, I made some recipes to solve the Bose-Hubbard model in strong coupling limit and made some recipes that how to construct partition function from the Hamiltonian and how in that recipe that we also concluded that we have to measure or introduce imaginary time, and then we just integrate out all that imaginary time and we get back to our desired result. So and also I stated that the best basis to use to solve this kind of problem in field theoretic way, that is a coherent state basis. And this coherent state basis is basically map a model from quantum to classical, or the classical and quantum correspondence are made by this coherent state basis problem. So now, in which theory do we have the coherent state basis? So in the model, the model which preserves the abelian gauge or the abelian theory, that model can be expressed as the coherent state basis or in terms of coherent state basis. But in the non-abelian thing, it is very difficult to construct the coherent state basis, and it is much more give you a trouble for the theory to construct that problem. So so we can start from the the title, that is the Bose-Hubbard model. So I mean to use some the mathematical digression of coherent state basis because it is very useful to know and learn uh, that property or the some claims or the proofs or the properties of the coherent state are basically used to solve in this model. So I do not repeatedly tell you that thing. So first I going through some mathematical digression for the coherent state and how the state is operated by the creation and annihilation operator, and after that we do our best measure. Okay, so first the for the single site, and for that moment we just drop the lattice index. So I just write this phi is the coherent state, which can be written as the e to the power phi b dagger of the vacuum state. So this zero is corresponds the vacuum state, and that means there is no bosons is sitting on that lattice point. So no bosons. And this phi belongs to a complex number. So it lies in the complex plane. So first claim one, that phi is eigenstate of the annihilation operator B, and dual space phi, that is the bra of phi, is the eigenstate of B dagger. So what does it mean? That if you apply operate B on this coherent state phi, then that gives you phi, and if you apply some B dagger on the bra phi, then you got that phi star phi. So this is our claims, and it can be proved very easily. It's a trivial thing. So as we know, this phi can be written in terms of the exponential of phi of B dagger, or maybe phi star of B. Then you just replace this phi in terms of the exponential and the vacuum state, and expand this exponential and do some very trivial calculation, and you get the same answer as I written here. So, and provided one thing may be very useful, it's your homework maybe, that you should do some B dagger to the n is given you that n B dagger n minus 1. So this may be useful result or the useful condition to prove these claims. So claim 1, this set of claim 1. So I don't waste our time to derive this or the make some proof of this B phi equal to phi and get phi of the coherent state. So if you face some difficulty to solve this, you can let me know. Then I can give you the solution of this, or maybe I can send you the proof of the claims that phi is the eigenstate of B, and so on. Okay, so what we basically do, there's claim 2. So which is very important, and some insightful information may be inherited here, so that I should discuss. And exactly using the claim 2, the claim, the overlap of the two coherent states is given by the overlap of two coherent state is given by, that is, phi and another phi, maybe phi prime, is basically e to the power phi star phi prime. So how do you do this? So proof, I just give some hint to prove this. So basically, as you have to obtain this inner product of two coherent states, which means some overlap in it, that you have to sandwich with the ground state or the vacuum state. So it should give you something phi star of B and e to the power phi prime of B dagger of sandwich by ground state. And what you have obtained, that if you expand to the n and this expand to the n, then one should may appear with some coefficient and something this kind of thing, that's Bn and B dagger to the power m of 0, and that leads you some Kronecker delta Mn of 0 Bn B dagger m and the vacuum state. So if you expand in some exponential in terms of a series, then you may uh, face the term, and after applying the condition of the Kronecker delta, and you end up your result that this is something e to the power phi star phi prime. And how that you may end up, this gives you something n, and this gives you something n, and here it's delta mn, and leads you something 1. So that is the basic thing. So what is the non-trivial things here? So maybe the trivial case I would suggest that if phi is equal to phi prime, then the overlap, then this overlap is basically non-zero. What does it mean? So that's mean these are coherent states are not orthogonal. So this is very important. These coherent states are not orthogonal basically. So because for phi equal to phi prime and phi, if you take some inner product, that gives you non-zero quantity. As you see, that's the phi prime and phi. So this is and this kind of non-orthogonal inner product basically means or leads you into the over complete basis. Over complete basis. That is the main reason that I have mentioned when in the first lecture that we can use the complete or the over complete basis, and then this over completeness of the coherent state because of the non-orthogonality between the two coherent states, and this is very fundamental issue of the coherent states. So now uh, I can give you some two fundamental comparison between some occupation number basis, that is the Fock basis, and the coherent state basis. And what is the Fock basis? Fock basis is something the occupation states are being defined by the state, by that state, and which tells us that how many number or the how many number of boson are occupied in that lattice point, and that is defined by this state. So occupation number occupation number basis is basically tells you that n m are delta mn, and this is a discrete countable number of states. So the discrete and countable basis on the number of states basically. And here we have compared this term that with the coherent state. We have seen that this phi and the phi prime, these are two coherent states, are basically a to the power phi star phi prime. So it is not the orthogonal set of bases, and this is the continuous over complete basis. So we haven't normalized this coherent state because as we try to normalize this, phi and phi are basically gives me that the phi square, which is not equal to 1. So basically it's not the normalizable thing or the normalized thing, and we can easily normalize, but it is not very important to normalize the coherent state. We can easily normalize. So how if you choose some coherent state that is e to the power minus half of phi square of phi, then we can normalize, but it is not very necessary thing to learn for this problem, and it has no necessary use for this problem. So I just mention it for the information. So now what is the main important, that the over completeness of the basis. So our claim 4, or sorry, claim 3, maybe claim 3, that is a completeness relation. So the completeness relation for these coherent states is given by that one is basically d phi star d phi over 2 pi I, as the states are lies in complex plane, so it's maybe a complete integral. So phi star and phi, that's the phi. So we can prove it very easily, that proof of this problem, the first you have to choose phi r e to the power I phi, or maybe I just given the phase. So as I give this kind of phase, so it turns out to be true that these bases are follow some U1 symmetry, so it's something isotropic, or it is consistent in the rotational symmetry. So that's why e to the power I theta is basically consistent, and the phase angle can also preserve the symmetry of the problem. So it does not change any kind of dimensionality or something else. So so phi star is basically r e to the power minus I theta. So now if we substitute, so d phi star d phi over 2 pi I e to the power phi square, the minus sign, sorry, I just missed the minus sign here. So phi phi is basically a problem of 1 by pi 0 to infinity or dr 0 to 2 pi for this phase angle, that is d theta e to the power minus r square phi phi. So if I apply the coherent state basis for this problem, that gives me 1 by pi sum over n and m, two dummy variables are basically 0 to infinity, then root over n factorial, root over m factorials are there for the expansion of the exponentials, and finding that r dr from 0 to infinity, and the rest of the thing are being very implied, that d theta e to the power minus r square r to the power n plus m e to the power I n minus m of theta and n m. So what I did here, so I just replace the coherent state basis or map the coherent state basis in terms of the occupation number basis, which is the Fock state basis, indeed I can say. Since this occupation number basis are the complete basis, that the outer product or the sum of the outer product of two occupation or the Fock basis are clearly gives us a 1 or the unity, so then it will turns out to be very simple, that it can give us the one identity and get some the result of the completeness relation of the coherent state. But in case that these coherent state basis, if I deals with the coherent state basis, that we have seen that these coherent state basis are not the complete basis set. So it's a over complete basis set. So that's why it no longer be a orthogonal set. So then it is very uh, difficult to handle that coherent state to prove this kind of completeness relation. So that's why I map this problem into a occupation basis set. So what should I do? To just I perform this integral and get the result, and it is very simple, I guess. You can see easily that these bases are clearly shows some gamma function in the polar coordinates. So I can easily set that thing, that as n are consist of the dummy indices, so I can use this delta function or the Kronecker delta relation, and then I can easily transform this into a single variable or the single index, that is the n, which runs from 0 to infinity 1 over n factorial, and that should be dr is something 2r e to the power minus r square r to the power n is the n m, right. So it is very easy to see that n and m are the outer product over there, and I just apply this Kronecker delta rule and rule out the m, that is the dummy indices, other dummy state. So I just give this problem here. So it is very easy to see. So now let's to perform this integral, you can substitute that z with z, that is the r square, and you can find that the dz is basically 2r dr, and what you ended up with this term, that n equal to 0 to infinity 1 over n factorial, that runs from dz, and it is the 0 to infinity, sorry, I just miss the limit of the integral. Okay, so it gives me to the power minus z, z to the n, and n, right. So as this integral is giving you something Gaussian integral, and this Gaussian integral and its divergence, it's not the divergence complete diverge anywhere, so it converts this integral into a n factorial, or so this part can be written as this gamma of n plus 1, and it will be treated as this integral is treated as a gamma function that should give you something n factorial. So this n factorial and n factorial getting cancelled out, and you end and stepping down this problem with something very simpler form, n equal to 0 to infinity sum and the outer product n times. And as these Fogg bases are the complete basis, so it gives you some unity. So it's a 1. So now I just prove this completeness relation of this problem, that completeness relation of the coherent state, that is very some coefficients are out there, and we just replace that coherent state basis in terms of the Fock state and make the bases are in the complete set, and get the very fruitful result and some our desired result. So that's it. So now I ensure you that why the coherent state is very useful tool to solve or make our problem simpler, and also it can map into a complex set of bases. So for the case of the Bose-Hubbard model, it is very easy to see that you can choose any kind of complete set of bases or the over complete set of bases, and for the that easy to see that the coherent states are the best basis to use to map from the quantum to classical description, and you get some desired result from there with the easy calculation. So, and there is no difference to take coherent state basis and the Fock state basis, because all are pretty similar. So uh, that could be done very easily. So now what we trying to do here, that our result in this section can be easily generalized in the Fock state or the product state basis. So these coherent states are can be generalized into a product state basis. So that can be written as some phi 1, phi 2, phi 3 times some phi n, maybe some the product state, and if I truncate it in n, so it may be some the product for the large number. So I can easily write this in this notation. And also, and if that it can be, if I write this in this form, then it is very easy to see that e to the power the exponential of this operator, that sum over I phi I bi should be applicable on the ground state or the vacuum state. So in this type, so these product states of the coherent state on different lattice site, it can be written as in this form, and what we get is the completeness relation that should be 1 equal to something. You have to take all the product states, so d phi star I d phi I over 2 pi I. Okay, so don't confuse with this, in this I and this I, it's some imaginary iota, and these I are the indices, which is the products, the product state indices, so don't confuse it. So and another part should be there, that minus I phi I star phi I, and our all the product states is like that, phi phi. So then the completeness relation is additional thing you can see for the product state. So completeness for the product state. So this will be the expression. Okay, so I think it is useful to know or learn how it look like. Or now so far so good. So I now generalize to how the Trotter formalism or the Trotter formula is can be written in the basis of the coherent state. So I can start from this problem. The so heading should be path integral representation of coherent state. Okay. So what we do here, so we use the coherent state basis phi to calculate the trace of to resolve the identities in the Trotter formula. So what we have to do to calculate in the coherent state basis of phi, to calculate the trace and resolve identities in the Trotter formula. Trotter formula. Okay, so as we have written that this partition function is basically the trace over e to the power minus beta h. H is beta is our some temperature, inverse temperature, and which is the in the same footing of the dimension of the imaginary time. So and this e to the power minus beta h comes from the canonical ensemble, which is something the ensemble average. So ensemble, what is the ensemble basically means that if you take some copies of the same system or the replicate or mimic the system for a large number, and that some physical quantities you want to know, that is the physical variable, that's the pressure, volume and temperature of the number, then you can easily trace out the all physical description of the physical quantities by taking average for the all this system. So you basically drive ended up or your conclusion into the macro state level. So from the micro state to macro state, and that average is known as the ensemble average. So ensemble average, from this canonical ensemble average, I can easily identify the partition function for the Hamiltonian, that the dimension of energy, that should be written as the trace over e to the power minus beta h, because h can be a matrix. So it is the thing, and I think it is very good and successful problem. So which should be some d phi star. So in the continuum basis, so that's why we have some integral over there. So and but the squeezing is like, so this looks like this. So now if you make some in slice of the time, the whole range of time, then our formula can be look like, so I can say that some delta tau is basically beta over n, because n is the number of time slicing. So how many slice you have made into the whole region of the imaginary time to define your path integral, that is the case, this beta n. So it should be d phi 0 star, that means the complex conjugate of d phi over 2 pi I, and that phi 0. So it's basically reveals that the ground state of the coherent basis, that's a phi 0. So e to the power minus beta h, and you just uh, making a slice of something minus beta h, and also in this form I should replace this beta with delta tau. So it's a basically a same dimension, so I can replace it where you say delta tau. So and in between you just squeezing the over complete bases, so you have a take a part of the over completeness, that is the 1 d phi star, maybe phi 1 and d phi 1 over 2 pi I. So e to the power minus phi 1 star, phi 1 and phi 1. So if you take some n number of times, so they are squeezing in the over complete bases are there. So maybe that should be a n number. So graphically you can easily see that if it is your dimension of beta, that is maybe something beta over n, or it is the dimension of tau, and here is phi. So you can construct something called a plane. So this kind of plane is discretized, or your time slicing description, and so on. So it's phi 0, phi 1 and phi n. So similarly you just rise up the level of the surface, and you can have some physical uh, schematic diagram in the time slicing, and how the quantum phenomena or the discretization maybe look like. So this is the game actually. Okay, so now what we uh, find here, that I just remove this part. So then the partition function is systematically looks like that if you product over alpha, that d phi alpha, d phi alpha, oh sorry, it's the complex conjugate, and 2 pi I, and your whole thing should be alpha phi alpha e to the power minus delta tau of h. So you can replace this beta with delta tau because this time slicing are tn plus 1 minus tn divided by n and so on. So this is the phi alpha. And also another thing it should have, that minus phi alpha star phi alpha. So that's it. That is the partition function. It's the partition function, and it's a classical description of the partition function of the quantum Hamiltonian in the coherent state basis, or maybe you can say the product basis of the coherent state. So that is how it looked like. Okay, so I just erase all the writings in the board because it's the lack of space of writing for the new thing. Okay, so evaluation of the matrix elements. So now evaluation of the matrix element. So how you evaluate the matrix element, that is phi alpha. So I just replace, no, nothing replace. So e to the power minus delta tau h of phi alpha plus 1. So this is our matrix element in the alpha and alpha plus 1. So what we can do, that I just, as the delta tau is the imaginary time scale and it's very small, so I can write by some expansion, that is 1 minus delta tau of h of phi alpha plus 1. So it's maybe look like something, look like this, 1 minus delta tau of h. So and do phi alpha and phi alpha plus 1, and provided this h should be function of phi alpha star phi alpha plus 1. So it's no longer be some operator description. So now it comes down into a field description, and it boils our classical, so boils our quantum description from there. So it's no longer be a Hamiltonian of a operator. So you can easily boils down this operator formalism from here. So that is the case actually. So e to the power minus delta tau of h phi alpha star phi alpha plus 1 plus phi alpha star phi alpha plus 1. So as this term gives you e to the power phi alpha star phi alpha plus 1. So since this inner product, so as the coherent state bases are over complete bases, and you know from the beginning of the lecture that this inner product gives you exponential of phi alpha star in the phi alpha 1, which is the eigenstate of, or sorry, eigenvalue of the coherent state, and you just ended up this matrix evaluation, so the element matrix element is look like in the coherent eigenvalue problem, and it basically description of the field actually. So pi is something called the field description, and it is indeed, so boils the quantum level to a classical level. So it's indeed a map between the quantum to classical level. So now what I do here, okay. Okay, so now the important matrix element should be phi alpha of h phi alpha plus 1. It should be important because we want to know the trace of Hamiltonian and how it's look like in the coherent state form. It should look like that phi alpha So I just write the Hamiltonian of the Bose-Hubbard model. Minus bi and that phi alpha plus 1. And now what should I do? So I know the claim 1 from the claim 1 that how the coherent state is operated or behave when the creation or the annihilation operator is acted on this coherent state or the operated on coherent state. So that should look like this. Phi alpha plus 1 and the coherent state eigenvalues maybe look like phi I star phi j, so it's alpha, maybe it's alpha plus 1 plus phi j alpha star phi I alpha plus 1. So it's become a hopping term, and minus mu I phi I alpha phi I alpha plus 1. It's a complex conjugate term. The dagger is operated on this, and this u by 2 sum over I phi I alpha star, that whole square, and phi I alpha plus 1, that whole square. So it is the form or sandwiched Hamiltonian in the coherent eigenvalues, in terms of the coherent eigenvalues in the classical description. And what we finally get, the partition function, is basically product of alphas of that. So integral also be under the product, that d phi alpha star d phi alpha over 2 pi I, and that should be exponential. That is the Hamiltonian part. So the exponential of sum over alphas, that phi alpha star phi alpha plus 1 minus phi alpha and minus delta tau of the Hamiltonian in terms of phi alpha star and the phi alpha plus 1. So it trivially looks like this. So now I used to move on to the continuum limit. Hopefully you can understand how do I make this part from the operator level to some field level. So what I do in the continuum limit, continuum limit in imaginary time direction. Imaginary time direction. So what will be the that phi alpha is something that phi of tau, and this delta tau maybe sum over the alpha delta tau. So the alpha is the indices of the time slicing, how many you have sliced the time range, and that moves into the continuum limits, which is 0 to beta d tau. So and another thing, that phi alpha plus 1 minus phi alpha divided by delta tau is basically gives you transforms into delta tau of phi of tau. So this is it. So and what we have in the partition function, that the partition function would be some the path integral over the coherent state basis. This is the phi star, and phi is basically e to the power minus s phi star of phi. So now this s is basically our action of this uh, Hamiltonian of the system. So action could be look like, so action could look like something 0 to beta d tau phi star of tau delta tau phi tau. I just substitute this continuum limit into the partition function in the product state, which I have written in few minutes ago, plus the Hamiltonian of the function of phi star tau and phi tau. That's it. So what will be the exact correct form for the Bose-Hubbard model if I place this Hamiltonian of the phi and phi uh, in terms of phi's, then how it will looks like. So it looks like, so this same is looks like for the Bose-Hubbard model, that sum over I integral 0 to beta d tau, and first term would be very simpler. So here is the minus for this canonical momenta. So phi I star delta tau phi I tau minus the on diagonal term is something phi I square is a function of tau maybe, plus u by 2 phi I of tau to the power 4, because it's a quadric term, and the hopping term would look like this minus t I and j is the nearest neighbor hopping 0 to beta 0 to beta d tau phi I star of tau phi j of tau plus phi j star of tau and phi I of tau. So this is the main action in the classical description for the Bose-Hubbard model, and you can see why the imaginary time is very needful here. So it's indeed needful because from the Hamiltonian, if you construct an action, then you move on to some Lagrangian formalism. So in the Lagrangian formalism, then you have some canonical momenta. So this field, this minus phi star del tau phi tau into the continuum limit, which is created from the path integral formalism in the time slicing method. So that is the analogous of the canonical momenta in the classical description for the Lagrangian. And you also think if you find some the quadratic action of this action from the Hamiltonian, you can easily determine the free energy. So in the free energy part, you may notice this the mu phi square and u by 2 phi to the power 4 and something the hopping terms are there in the Hamiltonian. From the Hamiltonian we obtained, and this is something uh, follows or preserved or the broke the Z2 symmetry. So due to the Z2 symmetry is spontaneously broken from this 5-4 theory, so we can easily uh, realize that the phase transition will occur here, and that is the Mi to SF phase transition. And I think, or I expect that phase transition would be a second order phase transition because the symmetry is not preserved here. So that is the main thing for the 5-4 theory. And what we notice here that in the lattice model, from the lattice model of the Hamiltonian, so Hamiltonian in the lattice model is discretized. So we uh, trying to understand the developed method uh, that given by some group of physicists and in the analytical description of the strong coupling approach, that we ended up to some field description, and this from by using this coherent state basis and obtaining this coherent state idea. And these phi's are typical analogy of the mean field. So if we create some Hamiltonian and making this effective Hamiltonian or the mean field Hamiltonian, then we easily find that the expectation of the annihilation operator is basically a field, which is the mean field, and we treat that mean field that the all points are basically identical, and all points exhibits the same phenomena of the model and also exhibits the same theory. From there we also create some the path integral formalism for that Hamiltonian, and making some continuum limit to continue discontinuous or something the discrete set of bases, and using this coherent state we end up our results or construct the action from for the path integral formalism. And this action should tell how the symmetry will be preserved or not and how the symmetry will be broken. So we may analyze or should analyze this the critical theory hopefully in the several class after some several class. So what I make some comment for today, that what we do in the next class. So I think it is the best point to uh, stop for progressing our uh, theory, because I think it should take some time to digest in you. So for the good digestion of this mathematical calculation or the insight, how do we approach here for to sell the problem into in terms of coherent state. So I think it is the best point to stop. But I before finishing, I just make want to make some comment or uh, make some share some idea of what will be uh, done in the next video or the next lecture. So I just completely erase the whole board and write something very, so it's a very dust, T with the chalk dust. So I think okay. So it's something the quantum field theory with complex field that phi I of tau belongs to a complex field, which corresponds that n equal to real compounds, which corresponds that n equal to 2 real compounds. And we could also take the continuum limit. So continuum limit in spatial direction that hopping will be produced as that hopping is produced as the spatial gradient. And in the terms of that gradient of phi, so r tau square. So that is the scenario we can easily understand from the path integral description. And also in the next class we will perform something Hubbard Stratonovich transformation. So basically this transformation is helps us to decouple the off diagonal thing. So what we do here, some Mott insulator forms because of the local repulsion. So I can easily and safely say that Mi phase or forms, so forms due to local, which is the strong actually, repulsion. So it's basically the strong coupling. And then in something derive the action that is phi star of phi in the interaction vertex in the phi 4 term. So I can see that the interaction vertex is in phi 4 term actually, which is proportional to u, and not expected to be small. So not expected to be small, uh, so close to or near to MISF transition. So near the phase transition, the expectation of the phi 4 term, that is the U, which is the on-site repulsion, is not very close, so small actually. And what is the goal actually? So goal of the problem. So just I erase this part to specify the goal actually. So why do we use the Hubbard-Shatner transformation, and it is very useful. So it is the main scenario why we can use this transformation. So, and how we use this transformation, that will be written in the 2 lines. That is the goal of our task. So goal is basically, first goal as a find a dual description in which the interaction vertex. So find dual description in which this phi 4 term are small. Secondly, that what does it mean? The strong coupling expansion. So as the hopping or tunneling strength is very small or weak in compared to the on-site repulsion, that is the strong coupling. So strong coupling, so we just partitively expand the hopping term. So strong coupling expansion around Mott limit, or the something you can say the atomic limit. Atomic limit, that is T by U is tending to 0. So in powers of T by U. So we just partitively expand the strong coupling expansion in powers of T by U, and we just take up to the order of quadratic order, so T square by U square or T by U square. So this is our goal, and we truncate our action into the perturbative expansion in the strong coupling regime. So we approach the superfluid from Mott insulating phase to superfluid phase. So we approach the superfluid phase from the Mott insulating phase. So basically, from the strong coupling regime, we start and see the critical hopping from where or the on which specific point the theory broke its symmetry, or the model broke its symmetry spontaneously, and um, step on the new phase, which is known as the superfluid phase. So, and last thing, which is the very important to solve, that we decouple the off diagonal term, in the lattice settings basically. that is site index, that is known as basically the hopping term. We know in the theory that of the Bose-Hubbard model, the hopping term is off diagonal. So we decouple the off diagonal term. So by using the Hubbard-Stationovich transformation. Okay, so this is so in the as we know in the mean field theory, so we use some mean field to decouple the off diagonal term of the Hamiltonian. So here we also decouple the off diagonal term by using Hubbard-Stationovich transformation in the path integral formalism in the strong coupling approach for the Bose-Hubbard model. So I think this is it, and the next class we just do this transformation and try to expand this Hamiltonian of the action up to second order by taking this quadratic order action. We truncate where we truncate our action in the expansion around the Mott limit, and from there we just find some correlator, which is the atomic limit Green's function. And after solving that Green's function, we ended up with some critical theory, which is the Landau-Ginzburg theory, and see how the system will behave on when the system broke its symmetry spontaneously and creates some new phase, or gives us a new phase or the new description of the model. So where the symmetry is broken, where the conserved quantity are no longer be conserved. So we will see in the next video or the next lecture. So for this so it is the best point to stop to digest whatever I taught in this lecture. So stay tuned for the next lecture, and thank you.